a much more fresh work than what Marcin was talking about. So this is a joint work with Iwan Blizniec, Marek Cygan, Paweł Komos and Lukasz Mach. And this paper will be actually presented SODA this year. And this is actually the first attempt to give a lower bound machinery for the positive result that we got on completion problems for classes, for subclasses of chordal graphs. So our main motivation is basically all this positive story that was presented before. So this positive story started with the work of Fomin and Wielange, who gave the first subexponential algorithm for completion to chordal graphs, also known as minimum fill-in. Then there was a paper of Koch et al., who gave it for split graphs, and it's actually a very nice and simple application of chromatic coding. Then we were able to manage to give such upper bounds, such algorithms for trivially perfect completion and for threshold completion. And finally, after a lot of struggle and after a lot of technical problems, we got it for interval graphs and for proper interval graphs. So as you may see from this picture, and also as Marcin said, almost all this positive result have running times of the form k to roughly square root k, apart from the one aberration of proper interval completion, for which we are stuck with k to 2/3 and we don't know what to do what to do next. So the natural question given this whole picture is why 2 to the square root k, or why roughly to the square root k? In the fine-grained complexity agenda, you should ask, maybe I can give a lower bound, possibly under ETH or under some other assumption, to show that this is actually a correct answer. Yes? So this is sort of mirrors the square root phenomenon that happens on planar graphs. So on planar graphs, also via the framework of bidimensionality, you can get a lot of algorithms with running time of type 2 to the square root k, and they usually come through the framework of bidimensionality, which can be traced to having square root and separators in planar graphs. And usually for these problems, when you look at the known NP hardness reduction, they just incur a quadratic blow-up in the instance size, which gives you an easy matching lower bound under ETH for this running time. So what about our completion problems? So unfortunately, life is not that easy for them. Namely, if you look at the known reductions for these problems, after cranking them a little bit and seeing how the parameters can be actually chosen, you can only give lower bounds of this form. Yeah, so there is a large gap between the known square root k upper bound and, say, k to 1/9 lower bound. And this was observed already by Fomin and Wielange in the first paper in this series. And yes, it is indeed frustrating that the known reductions do not give us tight lower bounds for these problems. And we actually believe that the square root k should be optimal for the following reasons. First and foremost, if you are able to break square root k here, then actually you have also a subexponential exact algorithm, because the number of edges that you can always complete to a click with roughly n square edges. Yes? And also, once you start working with these problems, you see that there is some fundamental trade-off between these expensive vertices and cheap vertices that Marcin was talking about. And this square root case really seems fundamental for this completion problems. So what we give in our paper is sort of a semi-satisfying answer, corroborating our suspicion that indeed this square root k should be optimum. Note for here that actually all the algorithms that we were talking about have running time k to square root k, which amounts to 2 to the square root k log k. Yes? So far we are not able even to pinpoint the right exponent of this k in the exponent. So for the purpose of this talk, I will just ignore polylog factors. If in my lower bounds I will lose some polylog of k in the exponent, it will be fine for me. So in my opinion, actually this log k in the exponent should be possible to shave off, and the correct answer should be simply 2 to the order of square root k. But as I said, so far we are very far from this goal. So actually, instead of thinking about trying to get this lower bound, yes, we will try to get simply a no subexponential exact algorithm for minimum fill-in throughout this talk. So what we were able to prove? Under the sole assumption of ETH, unfortunately, we only have suboptimal lower bounds. Namely, we can prove no to the square root n algorithm with losing some polylog n factors for chordal completion. And this, of course, translates to k to 1 over 4 lower bound. Yes, so there is still a gap between k to 1 over 4 and square root k that we know from upper bounds. However, we can also give some stronger assumptions that will be apparent in a moment, under which we can prove tight lower bounds. No subexponential algorithm and no nothing better than square root k. And the nice thing is that I have stated it here for the minimum fill-in problem, but actually the same lower bound machinery gives you the same lower bound for all the other completion problems that were mentioned before. Okay, so what we should start from, of course, is to look at the known reductions for the hardness of minimum fill-in and see where the problem lies. So this chain of reductions is from the 80s given by Yannakakis, and it proves NP hardness of minimum fill-in by a chain of reductions starting from FreeSat, then to MAXCUT, then to a problem called OLA, optimum linear arrangement, and then finally to fill-in. So the first reduction from FreeSat to MAXCUT is actually a very simple textbook example. This is a linear reduction that incurs no blow-up of the instance size. The problematic reduction is the middle one, from MAXCUT to OLA. So at least the reduction known in the literature incurs a cubic blow-up of the size of the vertex set, and also the output instance is not sparse. It actually has n to the 6 edges. And finally, the last reduction is also not that nice. Namely, when you look at it, it will incur a blow-up of size the maximum degree of the graph times the number of vertices. So if the graph here would be sparse, then this would be a linear reduction. However, as you see here, yes, this reduction before will not yield a sparse graph. Yes. So as you see, the biggest problem is probably somewhere here. So we need to focus first on this reduction. But before we look at this reduction, I need to actually define what is this optimum linear arrangement problem. So suppose you've got a graph, and suppose that somebody gave you a linear ordering of the vertices. So a mapping from the vertex set up to the numbers from 1 to n. Yes, a bijective mapping. So given an edge now, I can define its cost as simply the stretch, how it is stretching the ordering. Yes, so if the first vertex is mapped to 1 and the second vertex is mapped to 7, then the stretch is equal to 6. Yes, and this is the cost of my edge. And the cost of the ordering is simply the sum of the cost of edges, and the optimum linear arrangement problem asks for an ordering of minimum possible cost. Yes, so note that this minimum minimum possible cost can be as large as cubic. Yes, if you have a dense graph, because then you have n square edges, and each of them can have stretch up to n. Yes. Okay, so now let me look at reduction from the MAXCUT problem to the optimum linear arrangement problem, just to make sure we are on the same page. In the MAXCUT problem, I have a graph. I want to color it black and white, partition the vertices into two parts, in order to maximize the number of edges between the sides. Yes? So I take an instance of MAXCUT. This is a graph, and I take its complement. Then I add a huge clique of size polynomial, some n to c for a large number c. That is here, this is a clique, and it is fully adjacent to all the vertices in the complement of the input instance. Yes? And this is the whole reduction. So now let's analyze it. So if I'm given such a graph, how can the optimum linear arrangement of such a graph look like? Now, it is easy to observe that actually, because these vertices from the clique are twins, they have exactly the same close neighborhoods, you can assume that they will be consecutive in the ordering, which boils down to having the clique somewhere here and stuff on the left side and on the right side. Yes. So as we started from MAXCUT, I guess that you already see where I'm going to. Yes. So now I want to see what is the cost of this ordering. So instead of minimizing the cost of the ordering, let me do a trick. I will try to maximize the cost of the non-edges. Yeah, so if this was the whole instance was a click, then the cost would be something. Yes, and instead of minimizing the cost of the edges, I can maximize the cost that I do not pay for the non-edges. So where the non-edges can be here? This is a click, which is adjacent to the whole rest of the graph. So the non-edges can be either completely on the left, or completely on the right, or flying over the click. Yes? If they're completely on the left, their stretch is very small. Yeah, so they gain only a little, yeah, because it's length n. However, the click is huge. So every edge that is flying over the click will gain us a lot. And a lot more than an edge here. Yes, so if this click is really large, what the problem boils down to is to maximize the number of edges flying over the click, because they give us a lot. Yes? Which exactly is the MAXCUT problem. So in order this reduction to work, I need to have the property that every edge flying over the click gains us more than the whole total noise that can be incurred by the edges on the sides. And this is why I needed to choose this click to be large. Yes? Because if I can have quadratic number of non-edges here, in total they will incur total noise of n cubed, which means that I want to take the click to be cubic size. Okay, so this is the problem. Yes, this is why this reduction doesn't work a priori. So now what is our idea? And if you want to take something from this talk, this is the slide that you want to understand, because this is a very simple idea that will give us a better lower bound. So instead of starting with an arbitrary instance of MAXCUT, I will start with an instance that has a gap. Namely, let's consider the gap MAXCUT problem, where it is hard to distinguish between the optimum value being at most alpha, for some constant alpha times the number of edges, and optimum being larger than beta times m. Yes? So now, suppose that this problem is hard for some constants alpha, beta that are apart from each other. Yes? Let me now set the size of the click to be linear in n with this coefficient. Yes? So now, if I have this gap between the opts here in MAXCUT, how does it translate to a gap after after introducing this? So each, if I have beta minus alpha m edges in the gap, yes, if I multiply this by this number, the size of the click, then this will translate it to me to a gap of the cost twice n times m for the edges flying over the click. However, the total noise, the maximum noise on the left and on the right, is of size at most n times m. Yeah, because every edge can be stretched to length at most m. Yes, which means that this gap amortizes the noise. Yes, if I now map this instance or this instance by this reduction, then the gap is stretched and this noise here cannot bridge the whole gap. Yes? So if I am able to show hardness of gap MAXCUT for some notion of hardness, this reduction enables me to make a click only of linear size. Okay, so hardness of gap MAXCUT. First of all, falsification lemma gives me subexponential hardness of FreeSat in terms of the number of edges, of clauses. Then, if you apply the existence of almost linear PCPs that is known, this gives you actually a reduction from FreeSat to gap FreeSat. Yes, this is a problem of distinguishing a fully satisfiable instance of FreeSat from an instance where you can satisfy only at most r fraction of the clauses. And this reduction incurs only a polylog blowup in the instance size. So by combining these two facts, first falsification lemma and then almost linear PCPs, you get the following corollary. under ETH solely, you have some constant R that is bounded from 1 and a constant C, such that there is this hardness to the order of m over polylog m for gap FreeSat with a constant size gap. Yes? So this idea is actually not that new. It was already used by Daniel in 2007 for some work on geometric p-tasses. What is new in this work is actually using this idea of combining sparsification lemma and almost linear PCPs to have savings in the blow-ups of the reduction for NP-hard problems. Okay, so now you apply, using this corollary, you just apply the standard reduction from FreeSat to MAXCUT. You observe that this reduction preserves the gap, and you get this kind of hardness for gap MAXCUT, which, by using the stuff that I already presented on the last slide, give you this lower bound for OLA, which is like subexponential with losing a polylog factor. Good. So now how our situation looks now. So here we reduce from FreeSat to gap MAXCUT with polylog, with losing a polylog. Then we have a reduction from gap MAXCUT to OLA, which is gives an only linear blow-up of the instance size. However, we introduce a huge click. Yes? So the instance that we get here is not sparse. Yes? And finally, from here to fill-in, the reduction gives also a blow-up by the maximum degree of the graph. So we are still not yet there, yeah? Because this chain will incur a quadratic blow-up. Yes? So now this is the problem. Yes? So once more, we obtained a lower bound for OLA, but not on sparse graphs. And this is the problem, and this gives me only to the square root n over polylog and lower bound for minimum fill-in. And this is where we are stuck under the assumption of ETH only. So there are two routes to try to rescue this situation. First of all, you can try to show hardness of OLA on bounded degree graphs. Yes, this is a clear idea. And second, maybe this reduction can be made better. Yes? So let's look at plan 2 first. First, to show you that this is not that easy. Second, to show this reduction because this is a really elegant reduction. Okay, so this is a reduction of Yannakakis. And first I need to introduce some definitions. So a bipartite graph AB with bipartition AB will be called a chain graph if when I look at the vertices of A and I look at their neighborhoods in B, they form a chain in the inclusion order. So whenever I have two neighborhoods, one is contained into another. So equivalently, this holds when you look at B. You can prove it easily. And if they are ordered by, if they have this chain structure in the inclusion order, I can actually put an ordering on the vertices of A, so that whenever something is earlier in the ordering, then this is then its neighborhood is a superset of whatever is later in the ordering. Yes? If I now look from the B perspective, this is equivalent to saying that whenever I look at the neighborhood of vertex from B, then this is actually a prefix in this ordering in A. Yes? And now a chain completion problem is again the same kind of a problem. I get a graph, a bipartite graph, with a fixed bipartition. And now I want to add at most k edges to make it a chain graph. And when it comes to the lower bounds, actually this chain completion is like the mother of all completion problems, in the sense that you can reduce from this chain completion problem to all the completion problems very easily. For the reduction to chordal interval or proper interval completion, you just make both of the sides clicks. And you can show that if you have this co-bipartite graph, so a bipartite graph with both sides made into a click, the only way to complete it to chordal interval or proper interval graph is to make this adjacency between the sides a chain graph. And similarly, when you look at threshold and trivially perfect completion, you just need to make one of the sides a click. So it suffices to actually get a reduction from optimal linear arrangement to chain completion, because by applying this, you will get all the lower bounds that you want. Okay, so let's look at the reduction of Yannakakis. I get a graph that is an instance of OLA, of optimum linear arrangement. I just take one of the sides will be the vertices of the graph, second side will be the edges of the graph. Yes? And the adjacency is natural. Whenever I have an edge, I just connect it to the two vertices that are incident to this edge. So in other words, I take the graph, I subdivide every edge, and I put the subdivision vertices on one side and the original vertices on the second side. And this is the whole reduction. So let me, this is the whole reduction. Let me think about the optimum chain completion of this graph that I obtained. So if I complete it to a chain graph, I have some ordering on the A side, being the ordering on the vertex set of my original graph, such that the target order, this is this target ordering of the neighborhoods with respect to inclusion order. Yes? So how does it look like? So whenever I have this A side here, these are some vertices of the original graph. B side here, these are the edges of the original graph. And this is this order pi. Yes? Then every edge here was connected in my construction to two vertices here. Yes, the two original vertices. So now I need to make the neighborhood of this vertex a prefix of this ordering. So how many edges I need to add? Well, I need to add 2 edges. Yes, in this example. In general, I need to add the maximum of the indices of these 2 vertices minus 2 because I already have 2 vertices. Yes, because I need to make it a prefix with the minimum possible cost. So now comes the crucial observation of the proof, namely that you can express maximum of 2 numbers in terms of their sum and their difference. Yes? And you already see where I'm going because this is the cost in the OLA. Yes? So now if you assume that the input graph is regular, then actually the sum of all these summands will be constant because each pi of u and each pi of v, yes, will appear exactly the degree times by adding all of this together. Yes? So, and you can easily achieve that the input graph is regular by adding loops. This is just a technicality. So the minimization of the number of fill edges in the chain completion actually amounts to minimization of the OLA cost of this ordering pi, and we are done. Good. So now, having this reduction in mind, what we really would like to have is the sub-exponential hardness of optimum linear arrangement on bounded degree graphs. So the problem with the approach that we have is not only that we have introduced a huge clique, yeah, because probably the clique can be replaced with something sparse, like a sparse expander, but also by the fact that we complemented the MAXCUT instance. So we would need to actually prove hardness of MAXCUT in co-bounded degree graphs. Yes? So our approach here is that we introduce a new hypothesis based on minimum bisection problem and show that having this hypothesis, we can actually make the whole plan work and prove a sort of tight lower bound. So let me say a little bit about the min bisection problem. It's actually one of, in my opinion, most mysterious problems in computer science still. So I have the graph. I want to partition the vertices into 2 equal sides to minimize the number of edges between them. And this problem is NP-hard. It is, moreover, NP-hard and APX-hard on bounded degree graphs. Yes. However, the best known approximation algorithm, polynomial time approximation for this problem has factor log opt. So there is still a large gap between what is known and what is believed. The problem is FPT. This is just a side remark. We proved it a few years ago. And even on bounded degree graphs, there is not known any sub-exponential hardness of this problem under ETH. So it is perfectly okay with our knowledge so far that maybe on degree 10 graphs there is 2 to the squared an algorithm for min bisection. So we assume that this doesn't hold, and moreover we assume that gap min bisection is actually hard on some d-regular graphs. For some integer d and for some gap, there is no sub-exponential algorithm for the min bisection problem. This is our assumption. So in other words, you can think of it that for min bisection on bounded degree graphs, there is no sub-exponential time approximation scheme. Yes, this is sort of equivalent to this. So now, given this hypothesis, we can show optimum lower bound. So I will try to sketch what we are doing. So the first idea is to start with this mean bisection problem, which is sort of exactly this problem that we wanted in this reduction, and just replace the large clique that we had with a large constant degree expander to make the output graph have one degree. However, then we had this full joint between the clique and the rest of the graph. Yes, which also needs to be sparsified. Okay, so let's try the second attempt. So you need to be a lot more careful. Instead of one expander here, you put a chain of expanders, yes, that are somehow connected with each other, so that this whole structure is rigid. It will just be put like this in the optimum arrangement, and then you put the connections between the original graph and the expanders in such a way that this is balanced, in the sense that every vertex from the expander sees more or less the same number of vertices in the original graph, and every vertex of the original graph sees one vertex from each of the expanders. And this is in order to make sure that these neighborhoods are sort of uniformly distributed on K. So when we had a clique and a full join, everybody from all the sides just have seen the whole clique. And what we really want to do in the reduction is that whenever I have a vertex, it doesn't see just a part on one side of the expander. This neighborhood should be uniformly distributed in the ordering. Yes? So this is more or less what we do. This is really technical, and therefore I do not want to go into the details, but you need to make sure that all the parameters are set so that this reduction really works. And we used the fact that we started with a gap instance in order for the gap to swallow the noise on the sides in the same manner as in the reduction I have shown before. Okay, so let me conclude with some remarks. So we have proved suboptimal lower bounds under ETH, and have corroborated our suspicion that square root k is the optimum answer by showing this hardness under this minimum bisection hypothesis. So the message is not that we have actually proven tight lower bounds, but that now we have uncovered in a sense where the core of the problem lies, in this mean bisection problem. And we believe that this makes investigation of this hypothesis I have shown a really nice open problem to work on. So the same approach can be also used to get still suboptimal lower bounds for the feedback arcs in tournaments. This is under ETH only. However, under mean bisection, we cannot prove anything better. So still there is a gap for feedback arcs in tournaments using this approach. So some open problems. Definitely investigate the hypothesis. We believe that this is the core behind the hardness of the OLA problem and of the minimum fill-in problem. So we have so far seen implication only one direction, from the hypothesis to the OLA. Maybe there is actually some sort of equivalence between the hardness of the OLA problem and of the hypothesis. This would show that really the problem is in this approximation of mean bisection. Maybe there is some different route to minimum fill-in. Yeah? So we have just looked at the known chain of reductions. Maybe there is some different chain of reduction that shows NP hardness of fill-in that is better for working with the lower bounds. And finally, this is the problem that I actually started with when I was thinking about this project, namely the feedback arcs in tournaments. Once you look at this lower bound and see why you get only square root n and not n here, you see that there is a fundamental problem there. And we are so far unable to bridge this problem. Yes, and thank you for your attention.
So maybe it would be good to point out that if you have two graph classes A and B, such that A is a subset of B, like proper interval graphs, that A priori we don't know anything about the connection between the hardness of A completion and B completion.
Yeah, of course, because the target is different.
That maybe A completion is simpler because A is a subset, but what is it?
No, So, this is like...
Sorry, so do you know any particular examples where this is very counterintuitive or...
So let's look at the stuff that we started with.
The chordal interval and proper interval, the interval are the hardest because there are the ITs up there. They're sandwiched between the two of us.
Yes, yeah.
Length of proof or...
Yes.
In terms of... So I don't now have the full table of the ETH hardness of sub-exponential algorithms for this problem, but these are basically all the known things for which we have to the square root k.
There is another one, strongly chordal, right, between.
Strongly chordal?
Yeah. Between.
I don't know of any algorithm, a sub-exponential algorithm for strongly chordal.
I mean, that is something worth working on, right?
Yes, there are a few more classes where it is worth looking on. From the classes that may be worth is strongly chordal, chordal bipartite, and I think permutation graphs may have also a positive result, but I have not looked that much to it. But these are the classes for which we have k to the square root k. So in a sense, these are the like singularity points where we have k to square root k algorithm. And for all the other problems, whenever we are diverging from the framework of completion problem to a structurally defined subclass of chordal graphs, we have actually matching lower bounds under ETH showing that there is no possibility of getting sub-exponential parameterized algorithms. So whenever you have a class that is, for example, subclass of chordal graphs and for which we have this kind of reduction, for example, cluster graphs, which are much simpler, yes, and they are chordal. For them, we have no sub-exponential algorithm lower bound.
You mean
Yes, co-cluster, yeah, because we have for cluster deletion, we have matching lower bound. Yes.
So here for proper interval, you have k to the 2/3.
Yes, we have k to the k to the... Sorry? Yes, it's worse than for the interval. Yes, this is also.
The proper interval graphs are simpler, yet the best known algorithm is...
Yes. And yeah, this 2/3 just stems from the algorithm, from the technique that we have two-layer DP, and there is a fundamental trade-off that we cannot break so far.
Other questions? So I have one. If you assume ETH and the linear PCP conjecture, do you then get...
We are able to shave off this polylogs.
So then, does this imply your hypothesis for dissection?
No, meaning we don't know of. We don't know of. Under linear PCPs, we just shave off this polylog factor. Yes.
Okay, let's thank the speaker again.